again, as you saw when you were doing the assignment yesterday, it's important to keep a track of the difference between an arc, measure of an arc, and the measure of an angle. These don't have degree symbols on them, but we'll assume that they should have those on there. So WX, so this right here is 20 degrees, and arc XY is over here, that's 40 degrees. And arc UZ, so UZ, we'll assume it's the short one over here. So from here to here is going to be 108 degrees. And then UW, 108 degrees. And then UW, this one over here, is exactly the same as the one on this side. So we do know that the two of those are exactly the same. So since we've got from here to here, and from here to here, and from here to here, if we know the numbers for each one of those, we only have two missing arcs, which means we can add all of those up that we already have, subtract from 360, and we can figure out what's left for the two of them, and then we can divide by 2, and then we'd know what each one of them is. So if we add these up, this is going to be 168. We're going to take 360 and subtract that. So correct me if I'm wrong, we get 192, is that right? Oh, come on. 192? Okay, and then we have to divide that between the other two. So this is going to be, that means this arc over here, half of 192 is going to be 96. So 96 degrees right here, and this one's 96 degrees also. Now, we may or may not have had to figure out every single one of those, but like the one thing that's cool about this type of geometry is a tiny piece of information, and then the more you know, the more little tiny details that you can fill out. So let's take a look here. It says angle 1. Angle 1 is an inscribed angle. It happens to intersect an arc that's 96 degrees. So it's going to be half of the 96, so this is going to be 48 degrees. Angle 2 is right here. It intersects, and we wouldn't have needed to do any arithmetic for that one because they told us what XY is. That means this one's going to be 20 degrees. So 20 degrees right here. Angle 3 intersects this arc from U to Z, so that's 108, so we're going to take half. That's going to be 54 degrees. Angle 4 is right here. I don't know. How do I? D?
It's 106 if you add the two angles together and subtract.
Okay, so remember, I didn't write this down, but this one's 20, and this one is 48. So if you add the two of those together, that's 68 degrees, and then we'd subtract from 180. So what did you say we get?
It's supposed to be 54, right?
Oh, is it, oh, 54. Sorry about that. 54, yeah. 54, thanks. So, yeah, so 74? So 180 minus the 74 we've already used, so that's going to be 106. Everybody good there? Okay, and then angle 5 intersects this one right here. Angle 5 and angle 3 both intercept the arc from U to Z, so that one should also be 54. Okay, did I make any mistakes? Okay, what's the key when you draw a tangent to point U? If U is going to be the point of tangency, what's the key when you're drawing a tangent? Luke?
It needs to touch just U.
Yeah, it needs to touch just U. So it's pretty tough to do this perfectly, but we're going to make it look kind of like that. I'm going to put a big fat dot there, and then we're all set. Does anybody remember anything else about a tangent? Yeah.
Goes on forever.
A tangent line would go on forever. I'd take that. Yeah.
Well, actually, my answer is probably not.
DNJ? Oh, that's not a hand, that's a stretch. Okay. Nothing interesting about a tangent at U on this one unless we drew that line right there. Tangents are always perpendicular right here. Okay? They're always perpendicular.
Right.
Okay? They are. They are. Okay? Now, I actually gave something away. That's actually one of the more interesting things that we're going to talk about today is it is tangent. Now, all we did is we just drew a tangent. So we're going to come down here and we're going to take a look at a couple of other theorems, a couple of other pieces of information. If we know these, we can solve for more pieces. So this is called the intersecting chord theorem for angles. So the measure of an angle formed by two intersecting chords is half the sum of the arcs intercepted by the angle and its vertical angle. So if I'm doing this one, okay, so if I'm doing that one right there, and I want to know how big it is, I have to add AB and DC together, and I take half of that. So the measure of angle, oh, this would be angle 2. It would be half of the measure of arc AB plus the measure of arc DC. We take half that. Okay. The one I have right up above that is this one. So angle 1 is right here. So it intercepts this arc BC and this arc AD. And what I do is I add those two arcs together, so the one on this side and the one on that side, and then I take exactly half of that. Okay? So I add those together. Now, I'm not going to go through a proof, but I'm going to show you kind of a reason how you can see, oh, I can see why that would be. So everybody watch. I'm going to change colors, and this is what I'm going to do. So you can reason your way to a proof of this by sliding each one of those chords until it's a diameter, makes a central angle. So I'm going to slide this one so that it's like that. I'm just going to slide it over, keep it parallel to where it was before. I'm going to slide it over. And then I'm going to do the same thing with the other one. I'm going to slide it over here. Now, let's say, for the sake of argument, that now that it's at the middle, let's say that this is 100 degrees. What's the measure of this, the central angle? It would be 100 also. Okay? But if this is a 100-degree central angle, then that's a 100-degree central angle, which makes this arc over here a 100-degree arc. So if I added the two of those together, couldn't I say that the measure of angle 2 is 1/2 of the 100-degree arc plus the 100-degree arc? I get half of 200, I get right back to 100. Okay, that's not a proof, but that leads you in the direction of how you could prove that this theorem actually is true. Okay? All right, so if they intersect on the inside, you take the ones that the arcs that they intersect, you add them together, and then you take half that. All right? Okay, next one. Okay, this is called the intersecting chords theorem, and this one's kind of funky. It says when two chords intersect, the product of the lengths of the segment of one chord is equal to the product of the lengths of the segments of the other chord. So here's what this says. If they chop each other into pieces, into two pieces, you've got two chords, they're going to intersect in one place, they're going to chop each other into two pieces. You take the two pieces of this one, so x and y, multiply those together, it will be exactly the same as if you multiplied w and z together. Obscure piece of information. I'm going to change my color to green, and here's why it works. So you can reason your way to a proof by connecting the ends of the chords to make triangles, and then using vertical and inscribed angles to prove similarity. So I just want you to watch this. That's a description of what I'm going to show you. Now I'm just going to show it to you. So we're going to connect the endpoints like this. Okay, now the only thing that we know right now is that this angle would be congruent to that angle because they're vertical angles. Am I right about that? Okay. Now I'm going to highlight something over here, and I want you to think about it. Okay? That's an arc. It has a measurement. It's intercepted by angle Z. So since angle Z intercepts this arc right here, it would be exactly half of whatever that measurement is. You buy that? Okay. Now turn your attention to this one. Take a look at angle Y, or sorry, angle C. Doesn't angle C intersect the exact same arc? So if they intercept the same arc, aren't they congruent? Okay, so what I'm going to come back here and do is I'm going to say, look, I know that is congruent to that. Are the two triangles similar? Yes, they are. They're similar by angle-angle similarity. So what that means is, okay, I can compare W, whoops, I'll do it this way. I'll compare X to W, and if I compare X to W, I need to compare Z to Y. Those should be in the same proportion because those are corresponding sides. And if I solve that proportion, watch what happens. I multiply the X and Y together, I get X times Y. I multiply the W and the Z together, I get W times Z. Good? Okay. So luckily you don't have to worry about proving it. You just need to know that when it chops it into pieces, the product of these two pieces is equal to the product of these two pieces. And if you want to find the measure of one of those inside angles right here, you add the two arcs that intersects, the opposite arcs that intersects, and then you take half of that. Okay? So we're going to come down here and do a couple problems. Find the value of x using properties of chords. That happens to be an angle. It's inside here. So if you want to know what x is, we're going to take 1/2 of the two arcs that get intercepted by that and its vertical angle, the two opposite arcs if you want to think of it that way. So this is 45 plus 35. So this is half of 80. So that means x is 40 degrees.
What? That's crazy.
It is crazy. You'll notice that on this problem something is different on it.
It's swapped.
They switched it around. What we're looking for is the measure of an arc, but the same thing is true. So that angle on the inside, where the two chords intersect, 55 degrees would have to be equal to exactly half of the two arcs added together. So one of them is x, the other one is 86. I probably wouldn't want to distribute. I'd probably want to multiply everything by 2. So this is going to be 110. This is going to be x plus 86. Subtract the 86. So I end up with, am I right about 24?
Yeah.
Okay, all right. Put a box around that, we got it. Okay, don't say anything out loud. This one's different. We're not doing anything with angles here. Yeah.
Are you going to do like the comparing thing?
Yep, tell me what to write.
8/4 equals 6/x.
Okay, you're in the ballpark, but you've actually backed up a little bit too far. It's even easier than that. If we were going to compare them, we'd have to do 6 to 4 and 8 to x. So the easier way to get to this is just say, hey, I multiply the two pieces. 8 times 4 should be exactly the same as these two pieces multiplied together, so 6 times x. Okay? If you did it the way you said, the proportion we'd have to set up is 6, or I'll do 4 to 6. And if I do 4 to 6, I need to do x to 8. And if you'll notice, multiply by 8, multiply by 6, I end up with exactly the same thing. Okay.
But
Third, so I'm going to do this. I'm going to divide by 6. I'm going to do a little bit of cross canceling. 2 goes in here 3 times, 2 goes in here twice. I get 16/3 equals x. Raise your hand if you got 16/3.
I know.
All right, awesome. Okay? The next one's interesting. Okay? I'm going to give you 3 minutes.
Bro.
You can do it. Don't give up on it. We're dealing with pieces of the chords. Multiply the 2 pieces on one. Should equal the 2 pieces on the other multiplied together. Don't say no. Come on.
Now hold on a gosh darn minute.
Finished. I bet you got it wrong. For sure wrong.
How much was that group?
But yours, notebooks.
Okay.
I think I'm gonna throw a temper tantrum like I do it too.
Oh my god.
How does that work?
This is why we practice stuff like that.
Yeah, that's not the best part.
I know. I didn't even like find out the date. I just
Oh,
No, you sounded late.
I messed up. What was I supposed to
Close, what did you get?
I didn't get that.
Wait, what if they both work?
I think I got it right.
I don't know. What did you get? What's the
A negative number and a positive number.
Wilson, why don't you snowboard?
Can't be a negative sign.
Yes,
Yeah.
actually.
okay. That's about 2.5, 3 minutes. Check with the neighbor. Check with the neighbor. Compare your answers.
Wait, we can't do that.
Don't care which neighbor. If you need to get up and check with the neighbor, that's fine. If you need to slap D and J and say, what'd you get? Go ahead and slap D and J.
I got it wrong.
Crew got it wrong.
Crew got it wrong?
Because he didn't do it.
Yeah.
So he got it wrong. Crew doesn't do the notes. He just sits here and listens.
But I have an A in this.
That's what I do sometimes.
Yeah, I
It'll catch
Yeah,
up to
I
you.
do all the notes. It's so
True.
much easier.
True. That's what I did too. And I had
Catch
a
up to you.
Yeah, I got straight A's.
It'll catch up to you.
Yeah, I have all the hundreds on tests. And
It'll
so
catch up
that's
to
it.
you.
Because I
It'll
want
catch
to
up to you.
Well, then once you catch
Okay.
up to me, I'll do it.
Who thinks they know for a fact what the answer is? Raise your hand.
Wilson does not know.
Okay, keep your hand up if you want to explain it to everybody. Whoa. Lizzie, you're up. Okay, what do you think the answer is?
X equals 3.
What if somebody said I got two different answers and they got an answer of, what was the other one you got?
-8.
-8. Why can't -8 be an answer?
Well, you can't have a negative inside of a circle.
It doesn't go
You
into the
can't have a negative. What are we measuring here when we're looking at these? We're measuring lengths.
The side
Can
doesn't
you have a
go.
negative distance?
No.
Can't have a negative distance. Distances are always positive, so we throw that one out, and the answer is going to be 3. So Lizzie's right, that's the one we're going to keep. Okay, hold on. Listen up. Question.
Have a negative distance and just be imaginary.
Nope. Not in this, not in the real world. Okay.
Or be imaginary.
Okay, raise your hand if you knew you ended up with a quadratic and you kind of were in the right ballpark. Okay? Put them down. Okay? Raise your hand if you did this. This is what you did. You figured it out all the way. All right, not too bad. Okay, flip the page over. Okay, I said I jumped the gun just a little bit. If you take a look at the back side, there's a theorem about tangents to circles. So it says this. A tangent line to a line is tangent to a circle if and only if, we'll talk about that again, we've heard that phrasing before, if it is perpendicular to the radius drawn at the point of tangency. So what it means is this right here. If you've got a tangent line, if you draw the radius from the center to the point of tangency, it is always going to make a right angle. Okay? Now, when we see if and only if in a theorem, what it means is it is true whether it's read forwards or backwards. So hypothesis conclusion can be switched around. So here's what it means in this case. Okay? If it's perpendicular, so if it's tangent, then it's perpendicular to the radius. The opposite is also true. If it's perpendicular to the radius, then it's got to be a tangent. Okay?
Yes.
Assuming that it only touches in one point. All right? Now, if you want, okay, this is a little above board for a class like this. The easiest way to prove this is something called proof by contradiction. So you assume something that maybe it crosses in 2 points, and then they show that there's no way it can cross in 2 points, and it's got to cross in 1 point, and it's got to be perpendicular and stuff like that. If you want to look up a proof, there's a pretty quick little proof that's done right there. I think it's about 8 minutes long. Okay? So if we take a look at the last one, and this one we will kind of take a look at a brief little proof. Tangent segments drawn from the same external point are, you want to take a guess? There you go, congruent. Okay, they're congruent. So these pieces are the same. So what I want you to notice is, to me, it doesn't really look like that one is tangent. It looks like one of them is a, yep,
Will you please send Lockhart to the attendance office ready to check out?
yep, I will.
Thank you.
See you in like
What did
a
you
long
just
time.
produce to send it around?
Then they wouldn't give me popcorn on Fridays? Okay.
We'll go far.
So on this one, we can actually prove that this is true regardless of how it looks by doing this. If you draw a radius right here and right here, the thing we know from before is that this is perpendicular and that's perpendicular, okay?
Yes.
So then I'm going to draw this line from here right to the center. So I've augmented this. I've drawn some auxiliary lines. I've drawn 2 radii, and I've drawn a line from the external point to the center, and I've made 2 triangles. Okay, and what I have here is this. Those 2 are congruent. That one's congruent to itself. So this is something called hypotenuse leg. The hypotenuses are congruent, and a leg is congruent. That means these 2 triangles are congruent, so that means our conclusion would be this right here, which is what the theorem says, that those 2 sides, they've got to be congruent. Okay?
Side, side, side.
At this point, yeah, that's what that would be. Okay, so let's take a look at a couple of examples. Now, I will say this. I like the way these are drawn. I am not a fan of the way they're drawn on your worksheet. In fact, I'm going to lobby to change those next year. So it says this. AC, will you pull the door shut?
Yes.
AC is tangent to circle B at C. So if this is tangent, what do you automatically know? Yeah. It's perpendicular, which makes this what type of triangle? A right triangle, which means we can use the Pythagorean theorem. So we're going to have legs squared, and notice how I say this. You're not going to hear me say a squared plus b squared equals c squared. I'm going to remind you this is what the Pythagorean theorem works on. It works on a right triangle. Legs squared plus legs squared equals hypotenuse squared. And when we say hypotenuse, the only time you can have a hypotenuse is if you've got a right angle. Right triangle. Okay? So x squared, 144, 169. Move that over. Wilson's all happy because he's already done. What'd you get?
25, and then x equals 5.
Okay.
Gotta square it.
Okay, I'm going to put somebody on the spot here. I'm going to ask a question. Get that written down.
Yeah.
I'm going to ask somebody in here a question. I'm hoping you know the answer. Usually when we take a square root, we have to put a plus or minus in there. Why did we not put a plus or minus in there on this one, Zach?
Because.
Why not plus or minus 5? They both square to be 25.
Oh, because we can't have a negative in the circle.
Can't have a negative radius for a circle. We're talking a real length here, okay? So if we take a look at this one also a little bit more difficult, so take a look. That's BC is a tangent, so that's a right angle. Don't say anything. Set up the Pythagorean theorem.
I know what it is. Ah.
Dane's going to set it up for us. Dane, I need a leg squared.
Oh. 15 squared.
15 squared, I'm okay. Dane, I need another leg squared.
R squared.
Perfect. Dane, I need a hypotenuse squared.
R plus 9 squared.
Quantity squared, right?
Yeah.
Okay, don't say anything. Go ahead and square that. Don't say anything. Go ahead and square that.
Yeah.
225 r squared. Okay, I'll take a raise of hands. Does somebody tell me what this is when we square this out? It has a name. Don't tell me what the answer is. It has a name. And if you know the name of this and you know the pattern and you know the way these work, you're going to get the answer way quicker than somebody else because you're not going to have to write down two binomials and multiply them together. You're going to know that this is called a perfect trinomial square. So this is going to be a perfect square of the first one, a perfect square of the last one, multiply the two of them together and double it, so the middle term is 18r. Raise your hand if you got that correct thing on the right-hand side.
Not me.
Okay, take a look around. No, keep your hand up. Keep your hand up if you got that right. Take a look around. Okay. This is what kills people when you get to calculus. It's not the calculus ideas, it's the algebra, it's the trigonometry, it's the exponents, it's the logarithms. Those are the things that get in people's way because they can't remember, oh, that little detail, that thing that I learned in 7th grade or 9th grade, that was really important. Yeah, stuff like this is really important. Now, if you write this out as r plus 9 times r plus 9, you'll still get the 18r, but it's going to take you way longer to get it. Okay? Questions?
I have a comment.
Yes.
That's helpful. You gotta remember PEMDAS, parentheses first.
PEMDAS.
Exponent.
Okay, if that works for you, then that's great. Mason, did you have a question or comment?
Oh.
Okay. What's cool about this equation? There is something cool.
An answer that's
Yeah.
a whole number.
The r squared cancels out.
The r squareds go away. So I can move this over to the other side. So I can add 81 to this.
Minus
So,
81.
oh, subtract 81. Thank you very much. Subtract 81 from that, and I get
144.
144. And then over on this side, I have 18r. And what I'm really hoping is that 18 will go into 144. Does it?
Yeah.
Yes, it does. How many times?
7. I was guessing.
Make it cool.
8.
I was guessing. I got pretty close.
Pretty sure it goes 8. Okay?
It's 8.
All right. Any questions?
Do you know your 18 times series, Mr. Laws?
No. No. Okay?
What's your highest time, sir?
3. Okay. Tangent. What do you draw on there? Samara, what do you draw on here?
This English, that does not make any logical sense. Well, right there?
Yeah. If it's tangent, what do we draw?
Oh, the right.
The right angle.
I thought you
Okay.
It
Now.
says show.
You're right.
It doesn't say
So
it's
here's what this says. This says show that it's tangent. It doesn't say it is tangent, so we're going to put a right angle there and we're going to put a question mark. And then we need to remember something from 8th grade, and that is the Pythagorean theorem actually works both ways. If leg squared plus, or if it's a right triangle, then leg squared plus leg squared equals hypotenuse squared. But if leg squared plus leg squared equals hypotenuse squared, then it's a right triangle. So I'm going to do 9 squared
They do equal.
plus 12 squared. I'm going to put a big question mark here. Does it equal 15 squared?
Yes.
It does, because this is 81, this is 144, and we recognize these numbers from up above. So this is 225 equals 225. That checks out. So yes, tangent, because it's perpendicular. Okay?
What is this?
All right. Now, take a look at this one. Do not say anything out loud. Read the instructions. I realize it's a crappy drawing. But Caleb, what do we know about this?
We know that they're both tangents.
They are both tangents, correct, from the same point on the outside. So what do we know about how long they are?
They're the same.
They have to be exactly the same. Even if they don't look like it, they are exactly the same. So 2x plus 3 would have to equal 11. Move that over to the other side by subtracting. We get 2x equals 8. So x
4.
equals 4. Now, you do have to make sure that you're answering the question. Yesterday, we had a problem that said, find the measure of the angles. What does this one want us to do? Does it want us to find the measure of anything?
No, it just says X.
It just says find x. Did we find x?
Yes.
Yeah. Why would it be silly to say find the measure of those sides?
Because you can't find some of the measures.
Because if this one's 11, what's the other one?
11.
The other one's got to be 11. You could just look at it and say what the answer is. Okay, are there any questions? Okay, would you circle how you feel about this stuff right now before I give you the packet?
10 minutes.
Hooray!
I'm a little confused about
Kinda
that.
cool. I like it.
Well, it'd be cool if you actually did the. Yeah, those.
The what?
I got it.